what are isotopes? Isotopes are atoms, of the same element, but they have different masses. They are heavier or lighter versions of an element. The only reason they would be heavier or lighter would be if they had different numbers of neutrons. If we had different numbers of protons, well, then it's a different element altogether. And how do I tell you if I have a different mass than what I would usually have on the periodic table? Well, I would simply have to tell you. Or we have what's called isotope notation. So on that sheet that you've seen where there were a few that had like a dash and a number, well, that number just simply is a different mass. In most cases, what that rounds to is usually the mass of that element. But if I want to tell you I'm talking about a different mass, I've got to put a dash. So chlorine could have mass 37. Another way of writing chlorine would be with these two numbers on top of each other and then the symbol, where that's simply the atomic number and that's simply the mass. Which one is more common, a mass of 35 or 37 for chlorine? If you want to check what's more common, look at the periodic table. 35 is more common, but it could have a mass of 37 or 36, 34. Here are some isotopes of hydrogen. Which one is the most common type of hydrogen? Protium, deuterium, tritium. Yeah. If you look at the periodic table, hydrogen usually has just a mass of 1. Well, that should mean there's only one thing in the nucleus. So only a proton in the nucleus. So these are all technically hydrogen because they all have one proton. The proton, the number of protons is the thing that tells you what atom you have, what element you have. So it's one proton. Those all have to be hydrogens, but they are just different isotopes of hydrogen because these are obviously heavier. All right, so here's just simply a bunch of isotope notation examples, sort of like the sheet I've asked you to fill out. And I want to know all this info. So we're going to start with Jordan. If I write uranium-235, what's the mass? $235. Is that usually the mass of uranium? We gotta look. That was you. That was one of our bonus questions. It's usually 238. 238 is more common, but 235 is certainly possible, and that is our radioactive version of uranium. All right, Amanda, how many protons does uranium have? Just the protons. 92. Atomic number. The number of protons is not affected by the mass. We always can look up the periodic table of protons. All right, neutrons. Hopefully you got your calculators out still. Sailor, what do you got? Or how do you do it? Exactly. And you get? 143? Okay, that's the same as what we've done already. Mass minus protons. Just make sure you're using the correct mass. All right, and then lastly, Tom, how many electrons in uranium? 92. Since I haven't mentioned it's an ion, we're just going to make those match. Protons and electrons are just going to be the same. All right, let's see if we can go a little quicker. Ethan, what's the mass of phosphorus 32? 32. Will, look up phosphorus, which is P. How many protons? 15. Alan, how many neutrons? 17, good, just subtract. And Taylor, how many electrons? 15, got a match. All right, quicker. Shandini, silicon 30, what's the mass? 30. Katie, how many protons in silicon? 28. Okay, that 28 is the most common mass. There you go. But proton's going to be 14 always for silicon. Chase, how many neutrons?
5. No, 16.
Subtract 16. Kennedy, how many electrons? 14. All right. Now for these three, you still did need the periodic table to look up protons, but the nice thing about the bottom three is you don't. The protons are just the bottom number, the atomic number, so we can get all our info right from the notation. Alec, what's the mass of this isotope of iron? 58. Brian, how many protons in iron always? 26. Leah, how many neutrons? 32. Subtract. All right, Hannah, how many electrons? Just got a match, 26. Very good. All right, Noah, magnesium. What's the mass of this isotope? 26. James, how many protons in magnesium?
12.
Always 12. Emily, how many neutrons in this isotope? All right, 14. Eric, how many electrons? 12. Got a match. Mason, carbon. This isotope of carbon, what's the mass? 10. Blake, protons?
6.
Okay, let's stop shouting out random numbers and let the person I call on answer. Addison, neutrons?
4.
4. And Sarah, electrons? 6. Ta-da. Last class we learned I word number 1, which was what again? Isotopes. Okay, now it's time for I word number 2, ions. So in isotopes we talked about how the number of neutrons can change to make different isotopes of an atom. Now we're going to talk about how electrons can change. And that will create a different charge for an atom. And if you have gained or lost electrons in an atom, that's called an ion. So here's an example of sodium. Lovely Bohr model for us. How many electrons are on this outer ring? 1. And when we talk about atoms becoming ions, we actually really only care about the outermost or highest energy level electrons. And these are going to be called valence electrons. So, according to our Bohr model here, sodium's got 1 valence electron. Well, what was our rule before with drawing the Bohr models? Make it what?
Make it full or make it 8.
Make it full or make it 8. Okay, so we're on the 3rd energy level here, nowhere close to full, nowhere even close to 8. But if I could just get rid of that one, if we could just get rid of that 1 electron, well, how many electrons are on the ring underneath?
8.
8. Which in chemistry turns out to be sort of our magic stable number. Atoms really like to have electrons in sets of 8, or full energy levels. Even this 2 is stable on that first energy level because it's full. So sodium having this 1 little extra electron is really very unstable, and pure sodium is highly reactive. That's why you would not really find it in nature in its pure form. It would always be bonded with something else. So if sodium does lose this electron, it will become more stable. All right, so atoms will gain or lose electrons to make these sets of 8 to become stable. So 8, again, is sort of our magic number, except if we're talking about the really small elements, hydrogen, helium, even lithium or beryllium would want to lose to end up with just that little set of 2. So 2 is okay for the smallest elements. But sets of 8 sort of makes things stable. Now, another example, chlorine. All right, here's our Bohr model for chlorine. How many electrons are on this outermost level? 7. So this is called 7 valence electrons. The valence electrons are on the outside. 7 is not 8, obviously. So this is not stable as is, but it's so close to being stable that it actually is very, very reactive and will seek out this 1 extra electron. It'll try to take an electron from somewhere. And in fact, what might be a great pairing for chlorine that would give it 1 electron? Sodium, from the slide before. Sodium would like to get rid of an electron. Chlorine would like to get an electron. There's sort of a nice natural pairing. So once it gets this electron and it has 8 and it's stable, now it's considered an ion. So the valence electrons are what we care about to figure out how many electrons an atom will gain or lose. And there's sort of a little trick to figuring out valence electrons. And why is it valence electrons matter anyway? Why don't we care about the inner ones? So why don't we care about the inner electrons? Let's say you're in the hall, and the bell's rung, you're going to your next class, and there's tons of people in the hall. So you're probably going to bump into people in the hall. Is it your liver that's going to bump into them? No, it's not your insides.
Just go get a little bump. Just go get a little bump.
Probably not.
Just a little bump.
It's your skin. It's your outside that's going to bump into other people in the hall. So same with atoms. If they're going to react with different atoms or bond with different atoms, it's the outsides that are going to react or going to interact. So that's why we care about the valence electrons, the outermost energy level electrons. Now, the nice little trick is that you can actually pretty easily figure out how many valence electrons you have based on what group the atoms are in, the elements are in, from the periodic table. So group 1, and if you can kind of picture a Bohr model for hydrogen, all right, well, it's only got 1 electron, so I have 1 outermost electron. Lithium's got 3. Okay, well, that'd be 2 on the first, 1 on the next. So it's got 1 outermost electron. Same with sodium we just saw in the note. So everything in group 1 has got 1 valence electron. Everything in group 2 has got 2. Now we've got to learn our new model before we can do the transition metals. And sometimes they're sort of changing when we learn our orbital model theory as well. But skipping that for now, groups 13 through 18, you can also figure out valence electrons just by chopping off the 1. Everything in column 13 is not going to have 13 valence, but 3. Yeah?
No. Hydrogen only has 1 electron, but 1 valence electron. Like that.
It is the valence electron, yeah.
So, what if it does go away?
That can happen.
What happens to that?
Well, you would still have the proton. You'd still have, so 1 little proton
So it'd just be like a positive?
can be considered an ion of hydrogen. Yeah.
So it wouldn't have actually any electrons?
Correct. Yeah, we can still consider that an ion of hydrogen. It's the protons that tell us what we have. All right, so who loses, who gains? In the slide you saw sodium wanted to be a loser. Sodium just had that 1 extra valence electron it wanted to lose. Well, it turns out that the atoms that have only a few valence electrons are the losers. And those are the metals. Like when we did our metal project, everything's sort of on the left-hand side. Those are all your metals. Metals are losers. Metals are losers. Metals want to lose an electron so that their underneath shell, their underneath energy level is stable and full. The nonmetals that have valence electrons 5 through 7 want to gain electrons. It's easier for them to just gain a couple more to get to 8. So metals are losers, nonmetals are gainers, and the whole point is to try to get to the 8 valence electrons to be stable. Which actually means, if the whole point is to get to 8, what's the story about column 18?
They're great.
They're great. They already have 8. Except for helium, it's got 2. But they are in column 18. They're full, stable, happy. They have full valence sets, so they don't react. Is helium flammable? No, it's not.
It's just L.
Hydrogen is very flammable, very reactive. Helium, not at all. You don't ever hear of compounds of helium. I mean, hydrogen's in lots of things. H2O, you got hydrogen in water. You never hear of helium 2O, He2O, or there's no helium compounds out there. It does not react. It's already stable by itself. All right, so these are some of the questions I'm going to ask you to answer about ions. So sodium, this is a regular atom of sodium, and we're going to go. How many protons does sodium always have? 11. How many electrons would an atom of sodium have? Shh, wait, I'm asking Amanda. 11. You can tell by the picture. You could just know that an atom's going to have the same number because that's what makes it neutral. So if it's got 11 pluses and 11 negatives, what's the charge? 0. Atoms do not have a charge. Atoms are neutral. It's ions that have a charge. Now, we'll go ahead and answer these questions. Sodium being a metal, and just having this one extra, really wants to lose. So these are always associated. Metals are losers. Now, here's our ion of sodium, actually more stable than the atom of sodium. Mason, how many protons in this ion of sodium?
11.
11. Still going to be 11. Sodium got to be 11. How many electrons according to this picture?
11.
No. 10. We got 2 here, plus our 8. That's 10 electrons. So, what must the charge be? Positive or negative 1?
Negative.
Mason, what do you think?
I think it's positive.
It is positive. You've got 11 pluses and 10 minuses. So, and I know in math, if it was a positive number, you wouldn't really put the plus sign, but in science, we will. Put a little positive for anything that is positive, a little plus sign. And it's still the same answer. Sodium is a loser. It's a metal. It already did lose, but we will call it the loser and a metal. So this worksheet incorporates the 2 topics we have just studied, the 2 I words, which are what? Ions and isotopes. Let's go with those. So it's essentially atoms. But if they're isotopes, it means maybe they have a different mass than normal. We can have isotopes of oxygen, meaning they have different masses, different numbers of neutrons. Now we can also have ions where we have different number of electrons than a neutral atom would. And for all the bell work problems we've done, we've always said the same number of protons, the same number of electrons. Electrons and protons are equal. But that's not true in reality. That would rarely be true, because atoms are going to want to gain or lose electrons in order to become stable. All right, so here's our example number 1. It says oxygen-17.
Yeah.
Okay, and I want you to tell me all this info for this example. All right, so Mackenzie, I'm going to start with you. If this is oxygen, regardless of the mass or the picture I've drawn for it, there should always be how many protons in oxygen?
8.
8. And we all have our periodic tables, or we can look at the wall. 8. It's always going to be 8 for oxygen. Okay. Shh. No longer do I want you to say electrons is the same thing. It might be, but don't automatically just put that down as your answer. Well, why wouldn't you automatically put that down as your answer if you're given other information to tell you otherwise? And the other information I'm giving you to tell you otherwise is that A, this is a sheet of isotope and ion examples, and B, I've given you a picture. So use the picture. What are the dots in a Bohr model? What do they represent? Electrons. All right, so Colin, how many electrons do I have in this picture?
24.
10. And that's going to be kind of a common answer. And it's going to be a common answer because that's 2 full rings, and that's stable. So in this particular case, I've got 10 electrons. Neutral atom of oxygen would have 8 electrons, but this example's got 10. All right, next question, Bach. How can I get neutrons?
17 minus.
There you go, 17 minus 8. That is the mass I want you to use. I know you can look up the mass, but don't if I'm telling you a different mass. The mass is 17. We're going to do 17 minus 8, so that's going to give us 9. So we've got 9 neutrons in this isotope/ion of oxygen. All right, now new to us, charge. How are you going to figure out the charge?
If it's positive.
Yes, you've got to tell by the positives and the negatives. So I have 8 protons. Blake, are protons positive or negative?
Positive.
Positive. Are electrons positive or negative?
Huh?
What about electrons?
Negative.
Negative. All right, so Blake,
Yep.
if I've got 8 positives and 10 negatives.
Yeah.
What's the overall charge? 2. Positive or negative 2?
This
Negative.
no, negative.
Negative Ghost Rider. That'd be
Negative. It's negative because you have more negatives. If I got 10 negatives and 8 positives, the overall charge is negative 2. You might even want to go through your entire sheet and put the little pluses next to the protons and the little negatives next to electrons just to help you remember what's positive, what's negative. All right, now down to the gain or lose thing. You had 8 positives. You originally, as an atom, as a neutral atom, had 8 electrons, because these originally should match. But if it's not 8, it's up to 10. Well, you must have gained 2 more. Hence why your charge is negative 2. So I know this seems backwards, and I get a lot of people that confuse this every year. But a negative charge actually meant it gained. But of course, it's gaining a negative thing. So that's one thing I want you to write at the top of your paper to help you remember. Negative charge equals gain. And you should know this one for oxygen. Is oxygen a metal or a non-metal? Non-metal. So the gainers are going to be the non-metals. Now, on the other hand, a positive charge is a loser. I've taken away negatives, leaving behind a positive charge. So positive charge is actually because an atom has lost electrons, making it a positively charged ion, and the losers are the metals, with one exception. Do you remember which side of the periodic table we said was pretty much the metals side, left or right?
left.
The left. All right, looking at the left, what's our one over there that looks a little different? Hydrogen. Hydrogen is a loser. And in fact, that's kind of neat because hydrogen has how many electrons normally as an atom? 1. It will actually lose that 1. So it will lose that 1 electron to bond with other things to become stable. But it is not a metal. So except for hydrogen, which is a non-metal. Okay, so far so good. Let me do one more example. Okay, now we've got neon. And we have this different isotope notation with, these 2 little numbers on the side, one on the top, one on the bottom. And Mariah, how many protons would neon have? Always. 10. Now you could look that up on the periodic table, or conveniently, that's just that number. The bottom left number is the number of protons, so that's going to be 10.
Ow.
Brooke, how many neutrons in this isotope of neon? The top number is the mass, so you do 20 minus 10. So, 10. Again, top number is the mass. Now this actually is the same as the periodic table, doesn't mean it has to be, but this is the most common isotope of neon. All right, and then we're down to electrons. Now, unlike bell work, where we just said it was the same, although maybe it is, I want you to use the picture. So Alexa, according to the picture, how many electrons do I have for this isotope of neon? 10. Again, I said that would be a common answer because that's 2 and then 8. So 10. So in this case, Colin, what's the charge?
Neutral.
It is neutral. I got 10 pluses and 10 minuses. So that balances out. So it actually is a charge. So you have to cross that out. There is not a gain or loss answer there. Neon did not gain or lose. Neon was already stable as is. And that was true for any element in what column did we say?
18.
Yeah, column 18. All of those were actually stable already. So you'll never have ion forms of those atoms or of those elements. All right, but you can answer the bottom question. Is neon a metal or a non-metal? It's non-metal. It's in neon signs. It's a gas. It's not a metal.